It's a great day to do some story problems. You are going to need your graphing calculator for this section. It is 4.4. It got cut off up here. Okay, we'll start with this one right here, which is maximizing revenue. So they've given us a price P in dollars and a quantity X. So P is the price, quantity sold is X of this product. And they gave us the demand equation. So that's right here. So the price is going to be determined by the quantity sold. So we're supposed to find a model that expresses the revenue. Okay, well, revenue is going to be, let's see, revenue, of course, is going to be the price we sell something for times the quantity we sell. So they've already told us the price is this equation and the quantity sold is X. So revenue is going to be the price, negative 1/3 X, plus 100 times the quantity we sell, which is X. And if you distribute that X, we'll get an equation for revenue that it is negative 1/3 X squared plus 100X. So there's our revenue equation. Part B, what is the domain of R? We want to think about what the graph of R looks like, and then we'll talk about the domain. So part A and B, I'm going to draw a picture of this. This is a parabola, right? Because it's x squared, and it opens down because of that reflection of the x-axis, and it's got a compression of 1/3. I also could figure out its x-intercepts. So if I look at its x-intercepts by setting the equation equal to 0, I think I'll go from this format, set that equal to 0. Then I would get x equals 0 here, and negative 1/3 x plus 100 equals 0. So that would be 1/3 x equals 100, or x equals 300. So those are my x-intercepts. X equals 0, x equals 300. And I know my parabola opens down. So getting a little picture of this, x equals 0, x equals 300. Those are the x-intercepts. And the parabola opens down in some manner. So it looks like that. And remember that every ordered pair on this graph, every ordered pair represents an x-coordinate. The x-coordinate is the quantity sold. So the number sold is my x-coordinate, and the y-coordinate is R, revenue. So in order to look at domain, obviously for a parabola, the domain is going to be all real numbers. But in terms of this problem, we would be best served as a company if we looked at our domain in terms of the revenue being greater than or equal to 0, so that we're not actually just bleeding money, right? So when our revenue is greater than or equal to 0, that means the graph is above or on the x-axis. So that would be any x values between 0 and 300. So that domain would be from 0 to 300. Let's see what we have for part C. What is the revenue if 100 units are sold? So part C, that's a pretty easy one. If 100 units are sold, X is the number of units sold. So we're just going to sub in X equals 100. I won't take your time doing that. You can do that. Just sub in 100 for your X value. What quantity X maximizes revenue, and what is the maximum revenue? So maximizing revenue, if you notice on this graph, this parabola does indeed have a maximum. the maximum occurs at the vertex. And that's going to happen on every parabola that opens down, is that we have a maximum that occurs at the vertex. And we know how to find that maximum. We practiced it in section 3 with a standard form equation. The vertex is found by doing the opposite of b divided by 2a and then subbing in to get the y-coordinate. So in this case, if we use the opposite of b, that'd be negative 100 over 2 times a. So let's go part D here. X equals the opposite of b over 2 times a, which is negative 1/3. So that is negative 100 over negative 2/3. And that gives us a stacky fraction. So the way that I deal with those is I multiply by 3 to cancel out that 3 and multiply by 3 up here. So that is going to give me x equals negative 300 over negative 2, so 150. So I have 150 for my x coordinate, and for my y coordinate, I'm going to plug in 150 to my equation. So negative 1/3 times 150 squared plus 100 times 150, 7,500. So which part of this ordered pair is which? Well, remember that every ordered pair is the number sold and then the revenue. So what quantity maximizes revenue is 150. What is the maximum revenue? 7,500. So 150 for the first question, 7,500 for the second. And then what price should the company pay in order to maximize revenue? Well, that can't be answered from this ordered pair. To answer that question, we're going to have to go back and look at the price function, because this is the price that we're going to sell things at. So we would need to sub in our quantity sold, which is 150, to the price function. So we'll sub in 150 to the price equation. So part E, price would be negative 1/3 times 150 plus 100, which is negative 50 plus 100. So we're going to be selling these items for $50. All right, moving on. Number 10, enclosing the most area with a fence. So we've got a farmer that lives next to a highway, and they're going to be building a rectangular plot with 2,000 meters of fencing, but they're not going to fence the side along the highway. Don't ask me why that makes sense. So here's our highway, and our farmer is going to enclose the field with some fencing along 3 sides. They have 2,000 meters of fencing that they're going to use, and we want to maximize the area. So remember that area for a rectangle is going to be length times width, and I will label these width, width, length. So one key to setting up this problem is recognizing that we're not actually using the full perimeter of that rectangle to fence with the 2,000 feet or 2,000 meters, my bad. But what we are doing is saying that 2,000 meters would be equivalent to the length plus 2 widths, because we're not going to fence this other side. And what they want us to maximize is area. So find maximum area. Anytime I read that, anytime I see that word maximum or minimum, I'm thinking, about parabolas because they have a maximum if they open up and a minimum if they, I said that wrong. They have a maximum if they open down and a minimum if they open up. So that's kind of what I have in mind. But since my area is length times width, I'm going to need to get that down to only having one variable. So I'm going to use this relationship here to make a replacement. So in my area equals length times width, I'm going to be replacing one of those variables by using this formula. I think what I will do is replace the L because I know I can just subtract that 2W over and then I won't have to deal with any fractions. So that's my plan at the moment. I'm going to replace this L by doing some stuff over here. So I will subtract my 2W, and that gives me L equals 2000 minus 2W. So I can make that replacement here into this equation, 2000 minus 2W in for the L. So now I have the equation A equals 2000 minus 2L times W. If I distribute, just kidding, you guys, I need emotional support while I do these notes. I need you guys to be here to be like, no, that's the wrong letter. Anyway, gotta go in now. 2000 minus 2W. If I distribute that W, then I get A equals 2000 W minus 2W squared, or negative 2W squared plus 2000 W. There's my parabola, right? This is an upside down parabola because of the negative out in front here. So it is a parabola that opens down. Every ordered pair on here, the independent variable is the letter W. So that is going to be a width. The dependent variable is the area. So each ordered pair will be a width of my plot and an area of my plot. Notice that it opens down, so I have a maximum. So right up here is going to be the maximum area and the width that gives me that maximum area. It's at the vertex. And remember, we find the vertex by doing opposite B over 2A and then plug it in to get the y coordinate. So once we have our model there, finding the maximum is pretty straightforward. So we would do, instead of x equals, because it's a w, w equals the opposite of b, so negative 2000 over 2a, so 2 times negative 2. So w equals negative 2000 over negative 4, which is 500. Now they want us to give the largest area, so I'll take that value that I just got for W and plug it into my area formula, either version, either this original one or this ending one. So the area will be negative 2 times 500 squared plus 2000 times 500. Negative 2 times 500 squared plus 2000 times 500. So the area would be, good grief, 500,000, and that will be in square meters. Okay, what's next? Analyzing the motion of a projectile. So this is a pretty common application of a parabola because whenever you throw something, gravity acts to, start pulling that object to Earth, and that makes the path of the object look like a parabola. So, yeah, that's how it works. This time we are firing a projectile from a cliff that is 200 feet above the water. So here's my cliff. And I know that it is 200 feet above the water, and it has an inclination of 45 degrees to the horizontal with a muzzle velocity of 50 feet per second. Okay, so they told us all that information, and then they give us this equation. All of that information is already included in here. There's our 200. That's the height that we're firing it above the water. The 45 degree, don't worry about that. That's figured in there. The 50 feet per second, that's in here. This negative 32, that's the pull of gravity. Negative 32 feet per second squared. That's acceleration due to gravity. And so this equation takes into account all of that information. This gives us the path of the projectile. It is, in fact, a parabola. We got the x squared. And it has a negative coefficient, so it's indeed a parabola that opens down, which we would expect when we fire a projectile. So here's our projectile. We're going to fire the projectile. It's going to, at some point, splash down into the water. Let's get some water in here. Okay. Every ordered pair that is on this parabola has an x-coordinate and a y-coordinate. The x-coordinate, they tell us, what is x? X is the horizontal distance of the projectile from the face of the cliff. So we have horizontal distance from cliff. Oops, comma. So that's this distance, like how far are we away from the cliff? That makes sense for our x-coordinate. And then the y-coordinate, h, is the height of the projectile above the water. That's the y-coordinate. Height above water. So x-coordinate, y-coordinate. At what horizontal distance on part A is the height of the projectile at a maximum? Well, let's see. It appears that we have a maximum right here at the vertex. And how do we find a vertex when our parabola is in standard form? We do opposite b over 2a, and then we plug that in to get the y-coordinate. So we're going to do that work on the next piece of paper because it's kind of lengthy. So I left you a blank sheet. I don't know if it's on the back or if you're going to have to flip. I think it's on the next page, so you probably can see them both at the same time. So to find our maximum, our equation function, h of x equals negative 32 over 50 squared. I'm going to put my x squared next to it instead of in the numerator, plus x plus 200. Okay. Let's see. We are going to use our graphing calculator to do some magic with fractions. All right. So we need to be working through this little guy here, negative 32 over 50 squared times x squared plus x plus 200 once we get our opposite b over 2a. So we'll start with x equals the opposite of b. b is 1, so negative 1 over 2a. Well, a is this interesting fraction, negative 32 over 50 squared. So we're going to let our calculator figure that out. If you don't remember or never knew to get a fraction on your graphing calculator, you're going to push very specific buttons. So a fraction on the graphing calculator, is going to be the alpha button. It's green on mine, alpha. And then the y equals button. Okay. So we're going to go alpha, y equals, and then that gives us a menu. And we're going to select the first item. So alpha, y equals, and then the first item. And that gives us the option for a fraction. But you don't push that until you're ready to type your fraction in. But that's how you find it. Okay, so clear. When I go to figure this out, I'm going to do -1. Oh, I guess I do want the fraction. Alpha, y equals. Okay. -1 in my numerator. And then in my denominator, I want 2, and then I'm going to multiply that by another fraction. So I'm going to go alpha, y equals, get another fraction, -32 over 50 squared. Now, it probably wants me to close that parenthesis right there. So now that this looks exactly like what I'm supposed to be figuring out here, then I hit enter, and it's going to return a fraction to me. So that is 625 over 16. So the x coordinate is 625 over 16. That is going to be the horizontal distance from the cliff to this maximum point. But what they want to know, that is what they want to know for part A, at what horizontal distance from the face of the cliff is the height a maximum? So that would be 625 over 16, and it is in feet. And then part B wants to know to find the maximum height of the projectile. So once I know the x coordinate of my vertex, I'm going to plug it into the function to get the y coordinate. So here we have 625 over 16, and then we're going to plug in h of 625 over 16 to get the y coordinate. So that will be -32 over 50 squared times 625 over 16 squared plus 625 over 16 plus 200. And let me just tell you how fortunate we are to have calculators that can help us with this, because it's a lot of fraction work if you don't have this calculator. So we'll start by doing a fraction. So alpha y equals, we need -32 in the numerator, 50 squared in the denominator, and then we need to multiply that by another fraction, alpha y equals 625 in the numerator, 16 in the denominator, and that fraction is squared. Then we need to add our fraction again, alpha y equals 625 in the numerator, 16 in the denominator, and then plus 200. And once our calculator screen looks like what we have on our paper, hit enter, and that's going to give us 7,025 over 32. So that's the y coordinate of our vertex, which is going to be the maximum height that projectile reaches above water. So we had 32/16 here. So what? 625/16 here, and 7,025 over 32 here. So that is our maximum height, 7,025 over 32 feet. Okay. At what horizontal distance from the face of the cliff will the projectile strike the water? So when the projectile strikes the water, that's right here. And they want us to say what is x, what horizontal distance is it, and we need to know, we've got to be able to figure that out. So when it strikes the water, the height above the water is going to be 0. So we're going to be setting up the equation 0 equals our function, -32 x squared over 50 squared plus x plus 200. Then we'll solve that for x. I'm going to guess that doesn't factor. So we're probably going to be using the quadratic formula. So x equals the opposite of b, so -1 plus or minus the square root of b squared, so 1, minus 4 times a, which is -32 over 50 squared, times c, which is 200, and then all over 2 times a, which is -32 over 50 squared. Whoops. That just looks challenging, doesn't it? It's a good thing we have that calculator. Okay, here we go. I'm going to work through this discriminant first. So I'll do 1 minus 4 times fraction -32 over 50 squared times 200. That was 20. 281 over 25. Okay, so x equals -1 plus or minus square root of 281 over 25. I wonder if that has a perfect square. I don't think that 281 does. Nope, it does not. We'll work with that. We'll deal with that in a minute. And then over 2 times -32 over -50 squared would be -64 over whatever 50 squared is, 2,500. All right, let's see. I'm going to go out on a limb here and say that when you enter this in my math lab, it's going to let you put in a decimal instead of a fraction for this one. All the other ones, it has to have fractions. That's why I was going through all the, like, how to do all the stuff with fractions, because I know that it makes you do fractions. Yes, it's going to say round to the nearest foot. So you're good on just using decimals here. So the square root of 281 over 25 was 3.35. So if we do -1 plus that number, that gives me 2.35. But then I'm going to be dividing by a fraction, -64 over 2,500. That's going to give me a negative number. So I'm going to do -1 minus what I had for my radical divided by -64 over 2,500. And that gives me 129.96. So that's going to be approximately 130 feet. Letter D, we are supposed to graph the function and verify the answers that we had on our calculator. That's just good practice anyway. So if I were to graph my function, which was y equals -32 over 50 squared times x squared plus x plus 200. And then they give me a window. It says when x is between 0 and 200. We'll go to the window from 0 to 200. We already know the maximum height was 7,025 over 32. So I might just go to like 7,500 over 32 for my y max. 7,500 over 32, and then graph that. So there goes my projectile off the cliff and hitting the water. And then I can verify that by finding the maximum here. So second calc, find the maximum. Let's see. Go to the left bound, right bound, guess. That says 39.06 to 19.53. So hopefully 625 over 16 gives me that 39.06. Let's try 625 over 16. Yes. And then to verify the x-intercept, I actually have to change my window a little bit. Oops, not that part. That can stay 0. But my y-min needs to go below the axis so that I can find that x value, because it has to be able to see that it crossed over. So now I calculate my 0, left bound is here, right bound over here, guess right there. And it says, well, this guy says 170. Did I make a mistake in my computations here? I bet I did. Shoot. Okay, I'm going to go back and fix it because I don't want to be wrong. Good thing we verified, right? So 1 minus 4 times a, which was negative 32 over 50 squared. You guys probably caught my mistake earlier. Negative 32 over 50 squared. So now I'm trying to catch up with you. Negative 4 times a times c, which was 200. So that's what's in my radical. And I needed the negative 1 minus the square root of that. Enter. And then I needed, yeah, that's where my mistake was. And then I needed to divide that by the fraction negative 64 over 2,500. Oh, there we go. So I had a mistake earlier in my computations. So it's about 170 feet. So lesson learned, always check your answer by looking at the graph if you have access to a graphing calculator. I think we're going to pause here because I have to get ready for the day. It's like 7:10 a.m. So I'm going to end this video. We'll come back and do the suspension bridge problem. We're going to skip the Norman window, and then we're going to do that problem. So this next video should be shorter.